I'll not be speaking of deliberate deception here, but a simplistic false history has taken root in which the Copenhagen School, led by Niels Bohr, predicted entanglement. And again, that Einstein rejected and did not understand quantum mechanics. Also, that later experiments vindicated Copenhagen and proved Einstein wrong. None of these things are true. So let's get on. What is quantum mechanics? Quantum mechanics is a theory that deals with entities that are beyond our direct experience. Quantum mechanics obtains knowledge about these unexperienced entities by their effects on what is accessible to human perception. In terms of the accuracy of its predictions, quantum mechanics is by far the most successful theory of all time. In quantum mechanics, measurement is taken to be basic and hence unexplained. This is problematic because one would hope to have an explanation of measurement in physical terms. Quantum mechanics is beyond weird. There's no problem in physical theories involving very strange ideas. The difficulty with quantum mechanics is that the concepts are so strange that nobody can really make any sense of them at all. There's an audacious claim that quantum mechanics gives a complete description of the world, one which is incapable of improvement. Max Born and Werner Heisenberg made this claim at an important conference in 1927. They said that quantum mechanics was a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. Their confidence flies in the face of the founding principles of science, in which all theories are susceptible to radical change as new observational and experimental evidence arrives. In 1935, Einstein, together with Podolsky and Rosen, dropped a bombshell into the world of quantum physics. They assumed that quantum mechanics is correct in terms of its predictions, and they stated this explicitly in the first page of their paper. They also assumed that a physical theory should attempt to describe objective reality, and they even gave an explicit expression for this. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. We'll talk more about this later. They concluded either quantum mechanics is incomplete, which means local hidden variables, or our universe is non-local, but they rejected this possibility. I'll just give you a hint of the type of experiment they had in mind. Imagine a source and a pair of particles traveling in opposite directions towards regions A and B. By conservation of momentum, by measuring the momentum of the particle at A, we can predict with certainty the momentum of the particle at B. The particle at B therefore has a specific momentum. But of course, this depends on the validity of performing indirect measurements. Is this possible? Why did Einstein, Podolsky, and Rosen reject the possibility that the universe might be non-local? All theories of physics in the history of science prior to EPR were local. This even includes Newtonian mechanics, because although gravity is supposed to act instantaneously, the effects fall off so quickly that they can't be measured. Relativity theory seems to mandate locality, especially if regions A and B are space-like separated, because nothing can travel faster than light. There are many regions A remote from B, and all of them can seemingly affect experiments at B, and this seems to render science impossible. To their great credit, EPR were the first to raise non-locality as an explicit possibility. Niels Bohr was the first to respond to the EPR paper. He proposed a small tabletop thought experiment. The diagram shows a planned view of it. He concluded, of course there is, in a case like that just considered, no question of a mechanical disturbance of the system under investigation during the last critical stage of the measurement procedure. But even at this stage, there is essentially the question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. This assertion is utterly obscure. For example, Arthur Fine accuses Bohr of lapsing into positivist slogans and dogmas. Schrödinger made 3 incredibly detailed responses to the EPR paper. The first and third of them have the same title, and they focus on the separation between the systems. We'll consider these together. After that, we'll consider Schrödinger's magnificent and detailed survey paper, The Present Situation in Quantum Mechanics. This was written in German, so we'll be using Trimmer's authoritative translation into English. In his first paper, Schrödinger defines entanglement. He shows that entanglement is widespread throughout quantum mechanics and is much more widespread than the special case found by EPR. He says that 2 systems with wave functions psi1 and psi2 are unentangled if the combined system can be expressed as the product of these wave functions. Otherwise, the systems are entangled. Schrödinger calls attention to what the EPR have shown, namely, that if a pair of particles are allowed to interact and then fly apart, they become and remain entangled. The subsystems become disentangled only when a measurement is made on one of them, so that the combined wave function psi collapses into a product. Schrödinger comments, "It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of having no access to it. This paper does not aim at a solution to the paradox, it rather adds to it, if possible." In the same paper, Schrödinger makes a famous scholar's analogy. It seems to show that for a particle in distant system B must have definite values for both position and momentum, where one of these values is obtained indirectly using a measurement at A, and presuming that measurements at A have no influence on measurements at B. Unfortunately, this contradicts Heisenberg's uncertainty principle, where position and momentum can't both have exact values. I'll leave you to read Schrödinger's analogy for yourself. It was non-locality by means of entanglement that Schrödinger regarded as discomforting and paradoxical. Schrödinger opened this first paper by emphasizing the importance of entanglement. I will not call entanglement one, but rather the characteristic of quantum mechanics, the one that enforces its entire departure from classical lines of thought. We skip ahead to Schrödinger's third paper, which has the same title as the first. Schrödinger strengthens the above result by proving that it is occasionally possible for the experimenter at location A to drive the system at distant location B into any state he chooses, whereas an experimenter local to B, who can measure the system directly, cannot do this. That's really weird. He affirms that quantum mechanics as a theory predicts non-locality as a necessary and indispensable feature. He considers whether non-locality is true in nature and says, "I'm not satisfied about there yet being sufficient experimental evidence for that." And he tentatively suggests a modification to quantum mechanics that would eliminate its non-locality property without changing its predictions in the domain to which it's so far been tested. He turned out to be wrong in this. Schrödinger gives his attitude to non-locality in the closing paragraph of his paper. I suggest that these conclusions, unavoidable within the current theory but repugnant to some physicists, including the author, are caused by applying non-relativistic quantum mechanics beyond its legitimate range. An alternative possibility is indicated. Finally, we come to Schrödinger's extensive and thoroughgoing survey paper, The Present Situation in Quantum Mechanics. We'll be using the official translation into English by Don Trimmer, and we'll also be using his pagination. The paper introduces his well-known Schrödinger's cat thought experiment, but discussions of the survey paper frequently discuss this problem alone, and they tend to do so in a trivial manner, focusing on the whimsical. This is particularly in popular accounts. Schrödinger's cat highlights important issues. For example, what is the correct description, if any, of the state of the cat when it is sealed in the box? The answer is different depending on whether the cat is included as part of the quantum system under discussion. Schrödinger affirmed that the universe is real in the sense that it exists independently of us. And the project of science is to try and provide us with a mathematical model of this world that can be verified by observation and experiment. He gives the simple classical model of the hydrogen atom as consisting of two charged masses. There are several ways of expressing the variables of this system. For example, the components of the positions and momenta can be chosen. All of these could be specified independently, giving the state of the system at a given time. Quantum mechanics differs in an essential respect from classical physics in that it allows only half of these variables to be chosen freely, say the components of position. Once these have been specified, no more can be said about the state of the system. On the basis of experimental evidence, Schrödinger remarks that this novel feature is unlikely to disappear in any future theory. Mathematical models are either attempts to represent the universe, as Schrödinger and Einstein and his colleagues contend, or they are attempts to represent our experiences and measurements, as Bohr and the Copenhagen School contend. In either case, all such models are the imagined creations of fallible humans. In particular, psi is an imagined entity. Schrödinger is having fun here. Wave function psi is a creation of his own mind. He says that theories of physics should not be expected to be either complete or perfectly correct. Here, Schrödinger is clearly supporting Einstein over the contention of the Copenhagen School that quantum mechanics is necessarily complete. Schrödinger next asks what psi can tell us about the character of the world. Could it describe a world that consists of ensembles of systems of classical particles? He proves that it cannot. Schrödinger then asks, could psi describe a world whose constituents are in truth occasionally smeared out or blurred? When we are discussing the atomic level, then there is no particular evidence on which we can decide this question one way or another. But what of cats? His famous thought experiment follows. This is far too well known to be detailed here, but it's clear that Schrödinger, at least, believed that cats cannot be smeared out. Throughout the survey paper, Schrödinger expresses sharp criticisms of the Copenhagen interpretation. First, because it denies the reality of the world. Quote, we are told that no distinction is to be made between the state of a natural object and what I know about it, or perhaps better, what I can know about it if I go to some trouble. He gives an imaginary dialogue. How so? Surely a system must be in some sort of state. No, state is psi function. It's the maximal sum of knowledge. I didn't necessarily provide myself with this. I may have been lazy. Then the system is in no state. The second objection concerns the Copenhagen's insistence that psi gives a complete description of the world. But this means that the theory is dictating which measurements are in principle possible. This is contrary to the spirit of science, in which we make any measurements we want, and allow them, whatever they turn out to be, to dictate the theory. A discussion of Schrödinger's survey paper is almost complete. He gives a thorough discussion of the EPR paper. In a footnote, he credits EPR as inspiring his own work. He says that the publication of the EPR paper motivated the present, shall I say lecture or general confession. He shows that by choosing to make suitable measurements on a state of EPR entanglement, it can persist unaltered indefinitely. That's in section 14. He remains opposed to non-locality. Measurement on separated systems cannot influence one another. That would be magic. He asserts that the simplistic way time is represented as being perfectly sharp may be the cause of some of the paradoxes of quantum mechanics. Over 80 years have passed, and so far no one has succeeded in amending the concept of time in the theory in the manner suggested by Schrödinger. In 1949, a full 14 years later, Niels Bohr repeated his views entirely unaltered in a book in honor of Albert Einstein. He repeated the discussions of earlier thought experiments devised by Einstein. He claimed that he had won these debates, but it's now becoming more widely recognized that Einstein was concerned about the implications of quantum mechanics for non-locality, and that Bohr entirely failed to recognize this. Bohr repeated verbatim his previous obscure conclusion, and he regretted that he had not expressed himself more clearly in his earlier 1935 paper. He hoped that his present account would clarify matters in favor of his position, and he claimed this despite the lack of any fresh ideas in his present account. This is not very impressive. Eventually, it became possible to test entanglement and non-locality experimentally. This is due to one person, John Stuart Bell. His photo is shown on this biography by Andrew Whittaker. In 1964, Bell published a paper on the Einstein-Podolsky-Rosen paradox. He proved that all theories describing a local in character universe must satisfy a certain inequality, whereas quantum mechanics predicted that this inequality would be broken. He concluded that in a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Moreover, the signal involved must propagate instantaneously. He also stated, the example considered in this paper has the advantage that it requires little imagination to envisage the measurements involved actually being made. Bell had a wonderful sense of humor, and this often came out in his papers, no more so than in Bertlmann's Socks and the Nature of Reality. Bell's colleague Bertlmann invariably wore odd socks. So as soon as Bertlmann stepped into the room and Bell saw that one sock was pink, he could immediately conclude that the other was not pink. Bell's own sketch from the paper is shown here. Bell asked whether quantum entanglement and non-locality was akin to this, merely an immediate increase in knowledge. He wrote, "There is no accounting for tastes, but apart from that, there is no mystery here. And is not the EPR business just the same?" Bell proves that entanglement and non-locality are disanalogous to Bertlmann's socks. They are uniquely quantum facts, different from any classical actualities. It's very important to remember that Bell is trying to make a disanalogy. Too many people, including some scientists, mistakenly believe that Bell is trying to make an analogy between entanglement and Bertlmann's socks. I think that they get distracted by the charm and whimsicality of Bell's example. Bell understands Einstein, which his opponents do not, but Bell disagrees with Einstein. Bell finds Bohr incomprehensible. That's also in the paper. It took several years before Bell's ideas could be put to the test. Early experiments were inconclusive. In 1984, Alan Aspect and his team showed that Bell's inequality was broken by pairs of photons that had interacted at the source and were now space-like separated. The experimental setup is sketched here, and Bell was expecting this result. Space-like separation was achieved by having superfast switches, SA and SB, 12 meters apart. The switches operated about once every 20 nanoseconds, and during this time light can only travel 6 meters. Each switch directed its photon into one of two detectors, K and L, that measured polarization in a particular orientation. The results at A and B are correlated, despite the fact that no physical entity can travel fast enough to transmit a message between A and B. It would have to travel faster than light. The original experiment had the disadvantage that the switches switched periodically, and implausibly the two photons might somehow obtain information about this fact. So in 2018, Rausch et al. Used fluctuations in the light from two distant quasars to operate the switches. Experiments continue to close ever more fantastical loopholes, and they have been carried out with A and B separated by more than 20 kilometers. The conclusion we can draw is that our universe is indeed non-local. Travis Norson gives the clearest explanation, and I will quote from him now. Bell's theorem, then, taken to mean the proof that local hidden variable theories are wrong, must be understood as the second part of an overall two-part argument, the first part of which is the EPR argument. The EPR paper says that locality implies X, and Bell's inequality says that X implies conflict with experiment. Here X stands for something like local deterministic hidden variables, but somehow the logic is easier to grasp by suppressing this. Obviously, if X implies conflict with experiment, then X must be false, which means we cannot maintain locality, because locality entails X. Misconceptions about what Einstein, Schrödinger, Bell, and Aspect and others proved are still shockingly widespread. Here are some of the most common. First, the Aspect experiments prove that no deterministic account can be given of microphysical behavior. Second, that the Aspect experiments prove that quantum mechanics necessarily gives a complete picture of the universe. Third, the Aspect experiments vindicate the Copenhagen interpretation. Even worse, that these experiments prove irrealism. These are all false because one can use the de Broglie-Bohm interpretation of quantum mechanics, in which these are all false. Some would raise the objection at this point that de Broglie-Bohm theory cannot handle relativistic situations. There are two responses to this. First, that de Broglie-Bohm followers of their school are attempting to close this gap. And secondly, that no interpretation of quantum mechanics is fully consistent with relativity, at least so far as we know yet. Here is a timeline of what we've been discussing. In 1927, the Copenhagen School declares that quantum mechanics is complete. But they say that physics should abandon its attempt to understand the world and should merely provide some sort of calculus for predicting the results of experiments. As a result, they do not develop any intuitions about what is actually going on in the world. In fact, they even discourage this. And it's the opponents of Copenhagen who actually get down to the work of discovering entanglement and non-locality. The Copenhagen School really don't do anything at all. Even after the aspect experiments, they complacently pocket the results and say, aha, in effect, this is just what I predicted. There have been many misrepresentations of Einstein. First, Einstein rejected quantum mechanics. Einstein accepted quantum mechanics is supremely accurate in terms of predicting the results of experiments. And in the EPR paper, he explicitly made the assumption that quantum mechanics is correct. It was the vagueness and irrealism of Copenhagen that he objected to. Allegedly, Einstein proposed thought experiments with the hope of proving quantum mechanics wrong, and Bohr explained where Einstein was mistaken. Einstein was correct in developing thought experiments to point out that quantum mechanics was either incomplete or non-local, and to highlight the difficulties of the latter alternative. Bohr's responses were unclear and missed the point. There's a myth that Einstein made few useful contributions to quantum mechanics. But here they are. Finally, I want to discuss what these experiments mean in terms of the reality of the world. And we'll go back to the EPR criterion for reality, which begins if, without in any way disturbing a system, etc. As EPR clearly state in their paper, this is not an attempt to define reality. It merely gives a sufficient condition. Tim Maudlin points out in his paper and YouTube video, both called What Bell Did, this criterion must be true by virtue of the natural meaning of its words. But it just so happens that in our universe, goings on at point A do disturb the system at B. The criterion is moot. Bell robustly defends both the reality of the world and the true vocation of the physicist. He says, the aim remains to understand the world. To restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. A serious formulation will not exclude the big world outside the laboratory. Alan Aspect usually expressed himself cautiously, but in 2014 he said, the idea that one should give up the notion of physical reality is not one that I find convincing, because it seems to me that the role of a physicist is precisely to describe the reality of the world, and not just to be able to predict the results that show up on our measuring devices. Here are a few afterthoughts. Entanglements can contain any number of particles, not just two, as we discussed here in this video. Once one fully accepts non-locality, then there is no need to suppose that particles travelling faster than light are needed in order to transmit information from A to B. Entangled systems of particles are a single physical entity having a single state. Some people water this down and say that entanglements seem like a single physical entity, but I don't do this. I think the statement here is literally true. Entangled systems have their own unique category of being, totally unlike anything discovered previous to this. Tim Maudlin is explicit about this, and Eddington's earlier term, wavicles, hints at individual microscopic particles having a unique category of being. Well, thank you very much for getting through to the end. Part 2 of my latest book discusses entanglement in some detail, including some maths.